Okay everyone, welcome to the second screencast of Chapter 5. In this screencast we're going to get our final version of endogeneity. Our final fully specified version of omitted variable bias is another thing we've been calling it. And that's sort of been informal up to this point, but now we're officially going to be calling it omitted variable bias. And it's still the same problem from back from the first week of class. I want to know what is the effect of an increase in x, right, on y. How does that affect y, right? And the problem could be is if there's this third variable z, and if that variable z is correlated with both x and y, then leaving it out is going to cause bias. And we already know what that means. That means that the normal distribution of beta 1 hat is not going to be nice and centered on the truth. This is what we want. We want the distribution of beta 1 hat, right? This is the probability of any given beta 1 hat. That's what's on the vertical axis. And on the horizontal axis are different values of beta 1 hat. And this is the distribution. It's normal, right, because of the central limit theorem, with a mean of mu and a standard deviation, we'll just call it of sigma. And these two parameters are what we're interested in. The first one is, what is the mean? What is the mu? And if we are unbiased, then we know that the mean of the distribution, or another way of saying it, is the expectation of the beta 1 hat distribution equals the truth. So this is what we're concerned with. If there is a z that is omitted, that is correlated with x and y, then this is not true, and we have a problem. All right, and so we're going to fully specify that in this screencast. We're going to get very specific mathematically with what is going on, and most importantly, we're going to talk about which direction does this distribution get shifted off of the true value beta 1, the true effect of x on y. And that depends. And so we will have a formula at the end, and it's not one you have to memorize, but it is one of those that I think is helpful. So let's dive in here. So here is our current version of endogeneity. And endogeneity is when there is a correlation between the error term and x, right? Because in the basic model, and I'm going to just do a bivariate for now, this is what we've had up to Chapter 5, this bivariate model. And so the problem is that any z's, any other variables that are correlated with y but are not x are in the error term. So there's all sorts of other variables in the world, but the error term is all of the variables that affect y. A change in them would affect y, but they're not x itself. Okay, so that's a list of candidates that could cause us endogeneity. And then the next thing we care about is, are any of those z's, the ones that are in the error term, correlated with x? So we can shorthand that by just saying, is the correlation between the error term and our independent variable of interest, right? Which I'm going to put a 1 on it because eventually we're going to have multiple x's. This x1, is it not 0? If it's not 0, that means this error term is correlated with this x, and we have a problem. All right, so that's up to this point the way we've talked about endogeneity. So we've even referred to it as omitted variable bias without being too specific about what the precise definition of that is. But the basics are that there is a z, an omitted variable, that is causing bias. And it causes bias when it's correlated with y first, which means it's in the error term, and it's correlated with x. All right, so we're going to precisely define that here. We're going to need a little bit of notation here to make this work, because what we need to be able to do is talk about what would a perfect estimate of beta 1 look like, a perfect and true beta 1 hat, and what would a biased beta 1 hat looks like. So we need a little bit of notation to distinguish between the true beta 1 hat and the biased beta 1 hat. So in order to not get confused, we're going to add a little bit of notation here. So nu here, this Greek letter nu right here, is going to be the error in the true model. All right, so we're going to basically set up what is the perfect and true model, And then what is the bias model? So we needed a different notation. So nu is going to be the epsilon, the error term, but in the true model. All right. Then this epsilon is going to be the error in the model where there is omitted variable bias. All right. So again, for this set of slides, for this first part of the slides, I should say, the error in the true model, the one that doesn't have any bias, is nu, and the error in the model with omitted variable bias is epsilon. And then we're going to have a what's called an auxiliary regression. An auxiliary regression, it's not our main regression. It's not what is the effect of this x on y. It's not what is the effect of education on wages. It's not our primary question, but it's a tool that we're going to use because we already hopefully understand linear regressions pretty well. We're going to use the machinery of linear regression to help us understand linear regression even better. All right. And we do that by doing kind of a thought experiment called an auxiliary regression. It's not a regression we're going to actually run, but it's a way of thinking about the relationship between the omitted variable and the included variables. All right. And we're going to do that using a linear regression. In the same way that our main concern is the effect of x on y. It's really just what is the effect of one variable on another. We can do that with any sets of variables, all right? And we can do that using another regression. Now, the goal is different, and so the rules for that regression are a little bit different than our main rules, right? Than the ones we've been following. I need to get unbiased. I need to try to get the distribution of the beta 1 hat as small as possible. The rules for the auxiliary regression are a little different, but we can use it because we know how to interpret the coefficients of a regression really well, right? We know that, for example, beta 1 hat is the effect of a 1 unit increase in x on y. And we're going to do something similar, but so that we don't get confused by having a ton of betas in there. We're already going to have a bunch of betas, but so that we don't get confused between the betas, the coefficients, the slopes in the main model, and the auxiliary slopes, the auxiliary regression coefficients, we're going to call them deltas, just to keep things separate. And then tau here, this is going to be the error in that auxiliary regression. Okay. Again, it's a side regression, and you'll see what I mean as I go. But if you need to refer back to this slide, or you need to come back in the screencast to what were those definitions again, I just wanted to put everything here on one screen for you. So again, nu, error in the true model. Epsilon, the error in the model that has the omitted variable. Delta, coefficient, these are the slope coefficients in the auxiliary regression, and tau is the error term in the auxiliary regression. So let's put all this together. Oh, there's just a little pronunciation guide there. Most of you know your Greek letters either through being in different Greek organizations or just from having so many econ and finance classes, but there you go. All right, so here are the steps we're going to take. We're going to write a one dependent variable, two independent variable model. And this is going to be the true model. This is going to be correct. It's not going to have any omitted variable bias. It's not going to have any endogeneity. It's going to be correct. Then we're going to write another model that leaves out one of the IVs. So we're going to get rid of one of these in a second model. All right. Then we're going to use this tool of an auxiliary regression to see how the two IVs are related to one another. In one of the models, it's included both of them, but in the other one, it's omitted. All right, and we want to know then, are those two independent variables related to one another? And we're going to use a regression to do that. A regression is a tool we already know. We already know that it tells us the relationship between two variables. So we're just going to use it again as a tool. So we're going to do that next. And then the last thing we're going to do is we're going to use what we find here in step 3, and we're going to use some algebra in order to compare 1 and 2, right? So remember, this was the true model is 1. Then we're going to write a model that has an omitted variable. And then what we want to do is we want to know what are the consequences of omitting that variable. And so all of this machinery that we're going to use, it's going to blow up and get all sorts of crazy math for a second. But when we break it down at the very end, we're going to be left with a really nice, intuitive equation that will help us think through whether or not leaving out a variable causes omitted variable bias. And in what direction is that bias? That's the real benefit of doing it this way. All right, so here we go with that. So here's the true model. This is the one that we should have run. We should have had y as our dependent variable. X1 is our independent variable of interest. This is the one we really care about. And then X2 is a control variable that we need. Okay. Now we don't yet quite know why we need it. This is there's a circularity to this. I have to jump into the circle at some point and be able to explain it all. But this is an X that is correlated with Y and X1. I mean, that's a spoiler because that's where we're going with this. But if this X is correlated with these two, then we have a problem. All right. But in this version, we've included everything. All right. So this is an unbiased model. There is nothing left in the error term here. Here it's called nu. Before it's called epsilon. And we're going to go back to calling it epsilon later. But again, we need different notation here for just a moment. But there's nothing left in this nu. There's nothing correlated with Y that is not X1 or X2 that is also correlated with X1. So this is the true and perfect model. All right. And beta 1 is not 0, meaning X has an effect on Y, and beta 2 is not 0, meaning X2 has an effect on Y. All right, so this is our true model. And now we're going to make a possibly bad model, and we're going to see how the two compare to one another. So suppose another model omits the second independent variable X2. So from this one, we have the X2, it's included, and we're going to estimate a coefficient for it. But in this version, we don't have X2. We just have X1. And so I could have come up with even crazier notation, but instead I'm just going to call this is the intercept from the model where we omit X2, and this is the slope coefficient on X1, or the effect of a 1 unit increase in X1 on Y from the omitted model, from the model where we don't have X2. Ultimately, what we want to compare is the estimate of this beta 1, the beta 1 hat with the omitted X2, and the beta 1 hat from the one where we include X2. Right? That's where we're going to end at the end of this section. And we're going to say, how does the beta 1 hat from this model differ from the beta 1 hat from this model? Right? If there's no difference, then we don't have a problem. We don't have omitted variable bias. And so we're going to end up with a nice formula that will show us that. All right, so just to recap, here's the true model with the beta naught intercept, the beta 1 slope coefficient, beta 2 slope coefficient on X2. And what we're interested in is beta 1 hat from here and beta 1 hat omitted X2 from this model. So what is the relationship between X1 and X2? That's going to be important, right? Because if we've left it out of this model, where is it, right? Because remember what we said. Beta 2 hat here is not 0. That means X2 affects Y, okay? So if X2 affects Y and we leave it out, where is it? Well, of course, it's in the error term here. Everything that affects Y that is not X1 is in the error term. So X2 is over here in the error term. So it's very important we know what the relationship is between an X1 and X2, right? Because X2 here is our Z. It's the thing we've left out that is correlated with X possibly, and we know for a fact it's correlated with Y because I told you it was correlated with Y back here on this true model slide. All right, let me step back. So I want to know the relationship between two variables. Well, let's just use our old friend bivariate OLS. We already know how it works. We already know a lot about it. We could pick a different way of getting at it, but why do that? We already know OLS really well at this point in the semester. So here we go. So this relationship between X1 and X2, we're going to call that the auxiliary regression. All right, the auxiliary regression. So this is going to be a regression that we won't really run in reality, but it's a thought experiment that helps us think through the relationship of these two variables. So what we're going to do is we're going to throw one of these on the left-hand side as a temporary auxiliary dependent variable. It's not the one we really care about, but for this step, it's going to be in that spot. And then the other variable is going to be the independent variable. And here is what that looks like. So in this case, I put x2, the omitted variable, right, the one that's in the true model, but is not in the omitted variable model, on the left side, kind of standing in as the dependent variable. And then x1 is over here. And so what we really care about is delta 1. What is the correlation between x1 and x2, right? That was always what we cared about though, right? Because we know this x2 is in the error term, therefore that z is correlated with y. And now what I want to know is that z, that variable that I've left out, the x2 here, is it correlated with x1? And the value of delta 1 will tell me that, all right? So, and if delta 1 is 0, then x1 and x2 are not related, and I won't have omitted variable bias at the end of the day. So let's now take this auxiliary regression, this expression for x2, and here's where things start to get a little messy, and I'm going to plug it in for x2, right? So here is that auxiliary regression, x2i. I just means this is a variable that varies across people, so it gets a little sub I. I'm going to take this expression, it equals x2, and I'm going to substitute it in right here for x2. All right, that's all I'm doing in the next step. Again, take the auxiliary regression, which is an expression for x2, and plug it in here for x2. So here we go. So I do that right here. So this is x2, right? x2 equals this was the auxiliary regression. And now I'm going to multiply out. I'm just going to distribute this beta 2 across. So beta 2 times delta 0, beta 2 times delta 1 x1i, and beta 2 times tau sub I. So that's this step. I just substituted in for x2 right here, and then multiplied everything out. Now that I've multiplied everything out, I'm going to group terms. I want to get all my x1s together as one term. All right, and that's what this middle term here is. So I factored out an x1i from this term and this term. Those both have x1i's in them. And so I've now factored out the x1. And so that leaves me with this term, beta 1 plus beta 2 delta 1. And then what I'm left with is this original term over here, beta 2 times tau plus nu, and I'm left with beta naught, this part of the intercept, and then I'm left with this beta 2 times delta naught, right? Which was delta naught is the intercept from the auxiliary regression, and beta 2 is the correlation between x1 and x2. No, I'm sorry. Beta 2 is the correlation between x2 and y. Sorry about that. So I've grouped those here, the intercepty stuff here. I've grouped the slope coefficient-y stuff here with respect to x1, and then I've grouped the error term-y stuff, right? Remember the tau was the error term in the auxiliary regression. I've grouped those together over here. So this crazy thing is about to be useful for us because we're going to use it to precisely see where does omitted variable bias come from. Up to this point, we've said it comes from leaving out a z correlate with x and y, but we haven't really said why. Why does that push the beta 1 hat distribution off of the true beta 1? Why does the mean get moved off of the truth? And this is going to show us exactly why. All right. So this was the original bad regression, right? This is the one where x2 is omitted. All right. And what we have from that is this. All right. Notice there's no x2. x2 is omitted here. All right. So these are just the same regression, just written differently. This slope will be the same as this term. This slope coefficient will be the same, well, if I can highlight all of it, it may not let me, there we go, is the same as this term. And this is the same as this term. So what this is enabling us to do is to break apart what is happening within beta 1 when we omit x2. And that is because it's the beta 1 from the true model plus this stuff. And this is going to be important for us here. All right. So this is what we want to compare. We want to compare the beta 1 that we get from the true from the omitted variable model with this, which is the quote-unquote beta 1 from the true model. But we've now broken it up to see what the effect of these three different parts is. All right. Ideally, to have no bias, this would be true. The beta 1 from the omitted model would be equal to the beta 1 here plus beta 2 times delta 1. All right, so this is the requirement for being unbiased. It's another way of saying what is the condition for having unbiasedness, right? Up to now, all we've really been able to say is, well, the correlation between x1i and the error term from my model that I run needs to be 0. As we're going to see, this is going to tell us the same thing, but it's a lot more informative than what we had before. All right. So what we want to know is the beta 1 from the omitted model equal to this beta 1? Well, notice what would have to be true for that to happen? What would have to be true for just this part of the expression to be true? Well, of course, this has to be 0, right? So the true model has this, and the no omitted variable bias condition is this. When will this be true? Well, when this is 0. All right. So omitting x2 causes bias when this term is not 0. All right. So omitting x2 causes bias if one of these two terms is not 0. All right. So if beta 2 equals 0, if beta 2 doesn't equal 0, that means there is a correlation between x2 and y, right? If delta does not equal 0, then that means there's a correlation between x2 and x1. So this is really just shorthand for our two endogeneity questions. Is there a correlation between the omitted variable and y? If yes, beta 2 is not 0. Is there a correlation between x1 and x2? If delta 1 is not 0, the answer is yes. So if both of these are not 0, then this term is either positive or negative, and we have bias. The beta 1 hat we get here is going to not be centered on the true beta 1. But if either of these two is 0, then we're fine. All right. So if x2 is not correlated with y, if x2 is not correlated with y, beta 2 is 0. We're fine. Right? That means it's not in the error term, right? If x2 is not correlated with x1, then this is 0, and we're fine, right? You have to answer yes to both the endogeneity questions. Yes, the omitted variable is correlated with y. This is not 0. And yes, the omitted variable is correlated with the variable of interest. This is not 0. All right. So this is a shorthand way of thinking about bias, and it also gives us direction. All right. So I think I already just said this, but why not say it again? If y doesn't depend on x2, then beta 2 is 0, and we're fine. If x and y are completely unrelated, delta 1 is 0. And remember why that was. Where did this delta 1 come from? Let me step back to the auxiliary regression. Right? This is delta 1. It's the correlation between x1 and x2. So if delta 1 equals 0, then x1 and x2 are unrelated, and we're fine. So if either of these two terms is 0, then we don't have omitted variable bias. all right? And so dropping x2 won't cause a problem. This will be just fine, all right? Omitted variable bias is more complicated in models with more independent variables. Let's say we had 5 or 6, but the intuition is exactly the same. So let's look at an example here just to kind of nail this down. Does education support economic growth? All right. Okay, so what we're going to do first is we're going to look at this growth regression. So this data set from these two researchers has the average growth rate of a country from 1960 to 2000. And it also has the average years of education and the GDP per capita. That's the first control variable that is in the model. So these researchers were looking at what is the effect of average years of education on growth. All right. And so here is the first version of that model. All right. Right here, this first column. So GDP growth in 1960 is in the model. Average years of schooling is in the model. So what we're interested in, of course, is this information. Right? We're not really all that interested in this information or this information. This is just the intercept, the constant. We're not interested in that. We're not going to interpret it. We're not going to say if it's statistically significant. In a similar way, we don't usually interpret the control variables. Right? This is statistically significant, right? Because t is way bigger than 2, but we don't care. We're not interpreting that. We did not build this model to look at GDP in 1960. We built the model to look at average years of schooling. All right. This is just a control. It's just there to help us get a good estimate of beta 1 hat. So first, is it statistically significant? Yes. T is bigger than 2, so we can interpret it. So for every 1 year increase in average years of schooling, the growth rate in an economy goes up by 0.44. That's a big number. All right. That's a growth rate change of 0.44 is not insignificant. Average growth rates in developed economies are just 2 to 3%. So an increase of 0.44 is substantively significant. Let me just for a second talk about why did we control for GDP in 1960? Why was that a control? Well, what if we had left this out? What if we had left out GDP per capita in 1960? Notice that's basically how rich are people on average in a country. Well, of course, how rich people are in a country is so GDP per capita is obviously correlated with average years of education, right? Richer countries are going to probably have, on average, more years of education. But why would GDP per capita be correlated with growth, right? It's in here as a control. So these researchers obviously thought that if they left GDP per capita in the error term, it would be correlated with X and Y, all right? Well, here's why. The richer a country is, the slower its growth rate on average, because it's a growth rate, right? When you have, say, and think about an extreme crazy case, an economy that has $1 is its GDP. Well, if that economy goes from $1 to $2, that's a huge growth rate, right? The smaller you're starting out from, the higher the percentage growth rate can be. Whereas an economy like the US, which is trillions of dollars, well, getting a 3% growth on trillions of dollars, that's tough to do. That's a lot of money, all right? So growth rates are negatively correlated with GDP per capita, and average years of education are positively correlated with GDP per capita. But all that matters for us, or for these researchers, is that it's correlated with both, and that's why they included it. So I thought I'd just mention that. So back over here, we have the auxiliary regression, we have the regression they ran without math and science test scores. That's going to be the next variable we're going to add. And we said that this is statistically significant, and a 1 unit increase in average years of schooling leads to a 0.44% increase in GDP growth. So these researchers thought that possibly there's an omitted variable. Maybe it's math and science test scores that are correlated with both growth rates, right? The more STEM people you have educated in STEM, the higher your growth rate, and correlated with average years of schooling. Obviously, average years of schooling and math and science test scores are clearly going to be correlated, and it's very plausible that math and science test scores and GDP growth would be correlated. So that's now included in the model. and notice what happens here in this version of the model. Now let's go and check our statistical significance and substantive significance. Wow, now t is way less than 2. So this is not statistically significant, all right? And our resulting beta, well, we don't even interpret it because we're not statistically significant. So if we had left out this variable, if we had omitted math and science test scores, we would have thought we had a result, but we would only have gotten a result because we had a biased estimate of beta 1. All right. So omitted variable bias can give you results that are radically incorrect, both in terms of statistical significance and in terms of substantive significance. So we worry about it a lot. And this is just the interpretation there that you can have for your slides. T-statistic. All right. So they suspect omitted variable bias. I already talked through this. And so they wondered whether or not it was the type of class that mattered. I already kind of jumped ahead here. But let's look at 3 things. So let's look at, and remember, the thing we care about are these average test scores on math and science. Right? This is the omitted variable. So is it correlated with y? And then is it correlated with x? All right. This is just the initial bivariate relationship between economic growth and average years of schooling. All right, so let's look at these 3 scatter plots. So here, it doesn't really look like there's much of a correlation. There still could be after controlling for things, all right? But what we're interested in using the scatter plot for is the 2 endogeneity question. Is there likely a correlation between the omitted variable, average test scores, sorry, it's not drawn for me here, average test scores, is there a correlation between average test scores, the omitted variable, and average economic growth, the y? And then correspondingly, I would have probably put this also on the x-axis. I would have probably flipped this, but this is what Bailey does, and I'm going to just stick with that. Is there a correlation between the omitted variable, average test scores, and the x variable, average years of schooling? All right. So if both of these are plausibly not 0, and I would say that that's true, they're not both the 0, and we can kind of see that here in the correlation here, right? We can maybe imagine that might be a little too low, but you get the idea, right? Looks like a correlation. So by leaving out the test scores, we're going to have omitted variable bias. And so if test scores, not years of school, actually are the thing that explain economic growth, remember, notice what happened here. Economic growth wasn't explained very well by average years of schooling. It was more about the math and science test scores. All right. So by leaving that out, we would have had omitted variable bias. We would have been wrong. We would have said there was a significant coefficient, and we would have interpreted it. All right. So so why is there a significant coefficient on years of schooling in that first column? All right, it's because of the omitted variable bias. Again, I already said that. I forgot I had it all listed out in the slides, but it's good for you guys to have it because you can download the slides and you can walk through it, and everything is documented here. You don't have to try to furiously scribble down everything I'm saying because these are pretty complete at this point. So that's this right-hand column. And again, I already talked through that, so I'm just going to kind of move on at this point. Yeah, the coefficient here, you could interpret that, but remember, we built the model to look at this. So I, as a rule, don't interpret any other variables. I didn't build the model to interpret the effect of math and science test scores, all right? So I could, if I wanted to do that, I might have a problem. It might be biased, right? Because I didn't ask myself the question, are there things correlated with growth and math and science test scores, right? That's not what I built the model to do. I built the model to look at the effect of average years of schooling, all right? And so that's the one I'm going to interpret. If I see it's not statistically significant, then it's over. I don't go on and interpret it. I say I cannot reject the null hypothesis that beta 1 hat is 0. I cannot reject the null that average years of schooling has no effect on GDP GDP growth. All right. So that's the end of this screencast, and I'll see you guys in the next one.